This talk reveals the discovery of tiny chips of nanothermite in the World Trade Center dust from 9/11. Thermite is an incendiary compound invented in 1893 and is made by mixing powders of iron oxide and aluminum. Once ignited, the aluminum grabs the oxygen from the iron oxide. This reaction releases clouds of aluminum oxide and generates very high temperatures in the elemental iron. This high-temperature iron easily melts steel. Tiny spheres of iron were also discovered in the World Trade Center dust and are evidence that a thermite reaction took place on 9/11. Nanothermite, a highly engineered, energetic nanocomposite, was conceived around 1990 and by 2000 had been weaponized and was manufactured in large quantities in top-secret military laboratories. This nano form of thermite does not just burn extremely hot, it is explosive. In this video, Dr. Stephen Jones announces the publication of the recent paper, Active Thermitic Material Discovered in Dust from the 9/11 World Trade Center Catastrophe, published April 2009. The implications of this new peer-reviewed paper are profound. Stephen also updates us on various facets of the quest to repudiate the official conspiracy theory about 9/11 and describes current efforts to create a legitimate investigation with real subpoena power.
Stephen Earl Jones earned his bachelor's degree from Brigham Young University in 1973, graduating magna cum laude. He received his doctorate in physics from Vanderbilt University in 1978. His PhD research was conducted at the Stanford University Linear Accelerator Center and his postdoctoral research at Cornell University. He taught physics at BYU for over 20 years. In addition, from 1979 till 1985, he was a senior engineering specialist at the Idaho National Laboratory in Arco, Idaho. And from 1982 until 1991, he was principal investigator for experimental cold fusion for the U.S. Department of Energy Division of Advanced Research projects. From 1991 until 1993, Professor Jones researched fusion in condensed matter physics and deuterium for the U.S. Department of Energy and the Electric Power Research Institute. And since mid-2005, he has applied his scientific expertise to research on the destruction of the World Trade Center skyscrapers. He was a founding member of Scholars for 9/11 Truth, and in late 2006, he was instrumental in the establishment of Scholars for 9/11 Truth and Justice, dedicated to 9/11 research utilizing the scientific method. He is co-editor of the peer-reviewed Journal of 9/11 Studies. So I'm very honored and proud to present to you Dr. Stephen Jones.
Well, thank you all. It's a pleasure to be with you here in Sacramento. And as David mentioned, our paper on active thermitic material discovered in the World Trade Center dust has just been published earlier this month, and Jeanette McKinley explained how that dust was acquired, at least one of the samples. We report in this paper on 4 separate samples. As I provide a little introduction to this research that we've done on the World Trade Center dust, we all saw these voluminous clouds of dust that were produced as the buildings were destroyed. So we've looked at and probed very carefully, this team of scientists, 9 of us, looking at the dust to determine what information, and there's a great deal of information actually in the dust that tells us what happened that day. Information about the presence of an explosive or pyrotechnic material that has been ignored in the official reports. In fact, to my dismay, NIST, the National Institute of Standards and Technology, has in fact refused to look for explosive residues in the World Trade Center dust. But we have not. We have proceeded, and I like this quote from Mahatma Gandhi. He said, "When I despair," which I want us to avoid, so I bring this to your attention, "I remember that all through history, the way of truth and love has always won." That's a remarkable fact. "There have been tyrants and murderers, and for a time they seem invincible, but in the end they always fall. Think of it, always." I'm convinced that he's right about that, and that provides a great deal of hope. I would like to talk a little bit about the collapse of World Trade Center 7 and the destruction of the towers before getting into our detailed analysis of the material found in the World Trade Center dust. So here we have on the right, lower right, a photograph of the World Trade Center 7 building. It's obscured by dust. We're looking across the World Trade Center 7 plaza. It's interesting. This is in the afternoon, and if you look to the just to the right of center, that tall building is World Trade Center 7. And it collapsed about 7 hours after the collapse of the towers. You do not see there a raging inferno of fire because fires were rather limited from what could be seen external to the building, certainly. And they were random. And yet the building did collapse straight down, pretty much onto its footprint at about 5:20 p.m. in the afternoon on 9/11. Now the World Trade Center 7, here's a more distinct photograph now on the right, had 24 steel beam core columns and 57 perimeter columns. It was solidly built, as you might imagine. And here we will get to see the collapse of World Trade Center 7 on the left, and the collapse of a building, I believe that one is in Oslo, Norway, a known controlled demolition on the right with explosives. Okay, you can see how similar these appear from the videos that we have of the collapse of World Trade Center 7. Notice that it proceeds basically straight down, and we'll talk about the free fall during a period of time for World Trade Center 7 in a minute. It's noteworthy that the 9/11 Commission in their report failed to even mention the collapse of World Trade Center 7. Hence, we see already the need for a new investigation, a thorough investigation that will not ignore the collapse of Building 7. I support Jeanette McKinley and in her support for the New York City CAN referendum, and I've already contributed to that, and I hope that you will do that as well as we seek this new investigation. That's one avenue for an investigation with subpoena power, which is very important in this quest for a fair and open investigation. I'm also encouraged by President Obama as he says there will be more transparency. Let's hope that that is the case as we investigate again the events of 9/11. Now, NIST last August came out with a preliminary report, finally, after considerable delay, on the collapse of World Trade Center 7. And they said, quote, "Failure of a floor beam and fire is a rare event, and indeed there have been many building fires that have not resulted in even local failures of the floor system." They also admitted that there had never been a complete collapse due to fire, which is true. So here's what they stated as their challenge. The challenge was to determine if a fire-induced floor system failure could occur in WTC 7 under an ordinary building contents fire. Now, you see, they're explaining that they're looking for a fire-induced explanation for collapse of the building. Which already seems to have the blinders on. We keep hoping and encouraging them to look for residues of explosives. So, how did they proceed? Well, first of all, they did not test any of the steel in World Trade Center 7 to look for the effects that they could learn from actual hard physical evidence on the steel. Instead, they proceeded with computer modeling with parameters. These are adjustable inputs into the computer model. So basically, it's a black box. And one of the parameters or assumptions that they plugged in to their computer model was this. The steel was assumed in the FDS model to be thermally thin, thus no thermal conductivity was used. Now let me try to explain what they're talking about here. Let me go to this. No thermal conductivity was used. I happen to have with me here I brought along a rusty nail. It's kind of funny, I suppose, but there's reasons we'll get to later. If I started to heat this with a flame, it would slowly, the heat would slowly conduct across the metal, even though iron and steel are not very superconductors, they're very good conductors, but they do conduct heat. It's certainly not zero. And I would feel that heat after a short time. Maybe you've done that with a pin or a needle. As I've worked on slivers, I've had to heat up a needle with flame, and that heat transfers along the needle, stainless steel, for example, to my fingers quite quickly in just a few seconds. Well, what they did is they turned off the thermal conductivity. Now, nature won't let you do this, even if you are a national federal laboratory, under, incidentally, the Department of Commerce, I should point out. Okay. Now, secondly, another parameter that is an observation in their model, even after turning off the heat transport and burning office materials near this critical column, column 79, they said in their report, it appeared likely the critical damage state, in other words, the failure of this column, occurred between 3.5 and 4 hours. Now, burning office materials, we're talking about chairs, papers, carpet, desks. Some of you made a fire, a bonfire. Does it last 3.5 to 4 hours with immense heat? No, actually, from our experience. And NIST, interestingly, had previously published data on heat release during the burning of office materials. This is in one of their earlier reports, and you can see from the plot, there's two. The red is the FDS model. The black is experimental data. They don't line up exactly, but the point is that by 2,000 seconds, the fire is way down compared to what you had at about 600 seconds. 600 seconds is 1/6, it's about 10 minutes into the fire. So you see that by the time you get to 40 minutes, towards the end of the plot, then the heat is diminishing, just as you would expect if you built a campfire or even a bonfire. The fuel burns up rather rapidly, and you don't have anyone in the building continuing to push office materials towards this critical column to keep this fire going for 3.5 to 4 hours. Nevertheless, that is what they somehow assumed, that there would be this intense heat for that period of time. Again, the critical damage state occurred between 3.5 to 4 hours. Now, you can't just let the office material fires continue to burn when the experimental data shows that the heat diminishes rapidly after about 15 to 30 minutes. Secondly, you can't turn off the heat transport. In other words, the heat being conducted away from the critical column because there are connecting members connecting to these columns so that the heat is transported away. The conductivity is not zero. Now, in a computer model, you can do any crazy thing you want, but nature won't let you do this. And some of us feel very strongly that NIST should allow us to actually have their model so that we can test it and put in reasonable, realistic parameters. Predicting, of course, that if we do that, the building will not fail. Clearly, if it requires 3.5 hours of heating with no thermal conductivity, then when you put in some conductivity and reasonable values for the length of time for fires, then you'll get much different results. Now, in August, again, August 26th of 2008, physicist David Chandler and I both challenged NIST on their preliminary report, World Trade Center 7. For example, in the report, they said that they used a constant speed estimate in estimating the time for the fall of the World Trade Center 7. I pointed out this is not good physics. They also ignored an observed period of free fall, as David Chandler pointed out. So here's what David Chandler noticed. Now these are the dots are data points actually taken from videos of the fall of World Trade Center 7. And fitting a straight line over this portion, as you can see, fits the data points very well for a period of about 2¼ seconds. The acceleration works out to about 9.885 meters per second squared. The acceleration due to gravity is 9.81 meters per second squared. This is almost precisely the acceleration due to gravity. And we both, David and I, challenged NIST. This is a public meeting that is over the internet. It's kind of interesting. We sent in questions to NIST saying, look, your report, your preliminary report has some big flaws and oversights and apparent errors. Can you look into this? And they did look into it, and here's what NIST came up with. Now, if you can remember that a little bit, that fit to the data. NIST, red data points, red circled data points. And again, looking at the actual videos of the collapse of World Trade Center 7, they did a fit, which is the red line. And indeed, for a period of 2.25 seconds, just as observed by physicist David Chandler, NIST checked, and sure enough, there is free fall. Nothing in the way for over 2 seconds in the fall of World Trade Center 7. Now let's read what NIST says about this. This is their final report now, not in the preliminary report, but in their final report. I believe it was November of 2008, last year. And here's what they say. Quote, the slope of the velocity curve is approximately constant between 1.75 and 4.0 seconds. That's a time period of 2.25 seconds. A good straight line fit to the points in this range allowed open circles in the figure we just saw, allowed estimation of a constant downward acceleration during this time interval. Quoting NIST, this acceleration was 32.2 feet per second squared, 9.81 meters per second squared, equivalent to the acceleration of gravity g. Exactly, within experimental errors, the acceleration of gravity g. And then they go on. This free fall drop continued for approximately 8 stories, or 32 meters, 105 feet. So for over 100 feet, the building, as you look at the roof in both cases, is freely falling, nothing in the way. Now in the question and answer period, when David Chandler and I challenged NIST to their errors looking at the drop of the building, Shyam Sundar said, well, free fall would mean that there's nothing in the way, and that can't happen because as the building collapses, there's a lot of material in the way. I'm paraphrasing. That's basically what he said, and we agreed with that. But now, from the data, NIST is constrained to admit that there was free fall drop for a time period of 2¼ seconds, which doesn't sound like much, but when things are dropping over 100 feet at free fall, that is significant. So this demonstrates, this free fall drop, that there was nothing in the way. No beams, no structure, no concrete floors, no significant mass. Now, how do you get mass out of the way? Explosives. Is there any other way? They didn't answer. In a model in which you have the floors still there because you didn't use explosives, so the floors are intact, as the upper structure hits the floors below, the stationary floors, it slows down the structure. It's just like when you hit, this does happen to us occasionally, you hit something in the way of your car, perhaps a smaller car. It doesn't matter how small it is, it slows you down some. That's conservation of momentum. In order for there to be free fall, which means nothing slowing you down, it means there's nothing significant in the way. And they did not explain, they don't answer how this could happen, unfortunately. Now, I thought they would, after we caught them on their error, they admitted, they checked the data. Yes, there is free fall. It's amazing. You'd think they would change their conclusions. Instead, they simply assert without proof that this period of free fall for over 100 feet, followed by about 1.5 seconds of impeded fall, is consistent, that's their word, consistent with their results of global collapse, as they discuss in chapter 12 of their report. But in other words, they didn't change anything in chapter 12 of their report. They just said, oh, yeah, free fall, yeah, sure, that's consistent. Now, you know, a black box computer model, which no outsiders are allowed to test so far, we're hoping to get around that with, for instance, NYC-CAN, that commission should be able, hopefully, to get a release of this model. Do you think we're satisfied just to sit back and say, oh, well, sure, it's consistent, whatever you say, NIST. After all, you're a federally funded laboratory. We will believe whatever you tell us. We're not satisfied as scientists. I'm embarrassed, frankly, that NIST makes this assertion without proof. It is good that they at least admitted that there was free fall. These are some views of the World Trade Center dust. We see these remarkable red-gray chips, upper right, we'll talk about those some more, and remarkable spheres in abundance in the dust. Many of these are rich in iron and aluminum and silicon together, a very unusual combination, which is not from melting of steel in the towers because of the aluminum and silicon present in significant amounts in many of these droplets. Previously molten nature of these droplets is shown by the fact that they have formed into spheres. When you blast water in the air, it forms into spheres by surface tension. Liquid metals will do that as well. They form into spheres and then cool, and you find all these spheres just in very large quantities then in the World Trade Center dust. Now, here are some close-up photos of the red-gray chips. Can you see in the right-hand photo, you see the red side, and then the insert shows one of these red-gray chips turned on its side, so you can see red on one side and this shiny black-gray surface on the other. Very characteristic, very interesting. We find it in all the samples that we have examined so far of the World Trade Center dust, which is 6 samples by Dr. Ferrer and myself. 4 of these are reported on in this article. We keep looking at more samples. Others have observed these red-gray chips as well. This photo was taken by Mark Basil, a scientist in New Hampshire area, and he had samples sent directly to him, I know, of the World Trade Center dust. Also observed in France by Dr. Frédéric Henri Coignier. And you can see very clearly in this photomicrograph by Mark Basil, the red and the gray layers. Very distinctive, very unusual and striking. Now, this is the electron microscope and XEDS system used at Brigham Young University. Dr. Ferrer is the lab director. He does excellent science and checked and rechecked the data that went into this paper. Most of the photomicrographs and XEDS, well, certainly I took a lot of the photomicrographs through the optical microscope. He did most of the electron microscope, the SEM and BSE images that you'll find in the with this machine, that you'll find in this published paper. Okay, here's the paper as it appears now online. It is an open journal. We selected a journal that would allow us to publish a lot of data. There are something like 33 figures, I can't remember exactly, 33 figures, color, 25 pages. That's a long paper. And this journal was willing to work with us. It took a long time, a very tedious peer review process, many pages of peer review on the initial submission, followed by this paper. This is a photo of Niels Harrit, who became the first author, a long story there, and great fellow, professor, associate professor at the University of Copenhagen in Denmark. He's been speaking out in Europe, for instance, Denmark and Paris. I know he's spoken out on these results and on 9/11 in general. Of course, he's very skeptical of the official story of 9/11 and agrees with the conclusions of this paper, which are the red material in these chips is explosive or pyrotechnic material and should not have been in the buildings. That's his statement is this material should not be in a commercial office building, certainly not in these quantities, as we'll see, some 9+ tons of this red material in the World Trade Center dust, extrapolating and estimating, but that's a lot of material from what we've observed. I'll go through those numbers in a minute. We see these chips, the same characteristics as we'll see in all 4 samples. So we do a consistency check between the various collectors, and we see the same signature in all 4 samples. This is now proceeding to a higher magnification. This previous was an optical microscope. Proceeding to higher magnification in an electron microscope. We see the red layer here on top and the gray layer below. At this magnification, we can already look at and sample the red and gray layers to get an overview of the chemicals present. We use X-ray energy dispersive spectroscopy. That will be on the quiz. Please make note of it. And at first we look here at the gray layers, which show oxygen and iron very clearly, a small carbon peak. And the question arose, I had this question early on compared to now. Perhaps what we're seeing is rust in the gray side, and the other is, the red is just paint, so we're going to check that hypothesis. We check very clearly. Looking at the red layers, however, there is no zinc, no manganese seen either. The composition, the nominal composition of A36 steel, as used in the World Trade Center towers, has about, you see, 0.8 to 1.2% manganese. So where's the manganese? You look at that bottom plot, for example. These are the 4 samples showing the same, essentially the same chemical signature. The principal elements are the same. Anyway, no manganese and no zinc. It's starting to not look like steel from the buildings because of the lack of manganese, and not like paint either, not like primer paint, as we'll see, because of the lack of zinc. Notice the elements that are there. Carbon, significant peak. Oxygen, aluminum, silicon, and iron. Okay. The one peak, number 3, has a small amount of calcium, potassium, and sulfur, but that could be some contamination. Dr. Fair was very careful to break these, if you can imagine, these small chips, that he broke a piece and then looked at that fresh surface. There's so much calcium sulfate in the dust that you can still quite often see calcium and sulfur showing up just for that reason, because of the wallboard. Okay, now here's a paint, the primer paint used by Tenemec, supplied by Tenemec for the World Trade Center. We see that in the pigment, this is from Appendix D of NIST report. We get facts from NIST, and they simply report the pigment and the components in the primer paint, which is high in zinc, magnesium, aluminates, calcium, and so on. But the absence of zinc, again, shows that this is not the primer paint. Even Frank Greening admitted that, if you know Frank. Thank you, Frank. The zinc is not there. Let's go back. Zinc is not there. And others have said, well, maybe this is somehow, as the buildings fall, you just get a mix of, aluminum and zinc. Mixes up, and you get this wonderful red stuff. Sorry, where's the manganese, first of all, and where's the other junk that we find in the dust, which is zinc and chromium and calcium and so on in abundance. But you see, those are not seen in abundance. There's a little apparent contamination in 3, but the characteristic signature does not show any zinc or manganese. Now, as you'll read in our paper, which I hope you will read, let me ask for applause. How many have actually read at least part of this paper? Okay, that's good, but it's obviously not all. So I'd encourage you to read it. It's not hard to find. If you Google, for instance, Harriet, Open Chemical Physics Journal, it should pull it right up for you. Red gray chips is a good way to Google for this too. So I soaked some chips in paint solvent working with Dr. Fair. We found, this is one of the early tests we did, the chip does not dissolve. Now, paint, which we also soaked in, I bought the solvent, it's methyl ethyl ketone, purchased it at a hardware store, it's a paint solvent. So I put chips of paint in there and they dissolved. Certainly the paint got flimsy and then you see dissolving, dissolution. But these chips did not dissolve at all. And there's no zinc, and now this, it's just not paint. Instead, what you see in these photographs is that the red portion swelled. The gray-black portion did not seem to be affected by the solvent at all. The red portion swelled, and can you see in the right photo the porosity that's now evident in the chip, the red material? And perhaps you can notice that there's some red material, and then with pores, this is primarily silicon dioxide, silica, with some iron oxide mixed in. And then in the left-hand side of this photo, the right photo, you see a silvery region. We found that the aluminum, elemental aluminum, separated out under the action of this paint solvent. Very interesting. Remember, there's a lot of carbon in here. The carbon does seem to break down. Okay, let's look at the data. Getting ahead of myself. This is in the paper. After the MEK soak, we now see regions where we see aluminum separated from silicon and oxygen. So if you look at the leftmost plot, you see a region, you see the silicon and oxygen, a little bit of iron, essentially no aluminum. This is not aluminum silicate. It's not kaolinite, as some debunker said. Oh, it's kaolinite, that's all it is. No, you can't use a paint solvent and separate the aluminum from the silicon oxide in an aluminosilicate. It's just a solvent. It's not a reducing agent, okay? So, and now if you look at the middle plot, you see a large peak of aluminum, very little silicon. Again, this is not an aluminosilicate because the aluminum has now increased dramatically, just has been pulled out of this matrix of stuff in the red material. The oxygen is much less than the aluminum, and we deduced, Dr. Fair is an expert in this machine, that the aluminum content exceeds the oxygen content significantly, and so there must be at least some elemental aluminum, which is one of the prime ingredients of thermite. There is also iron oxide, as shown in the rightmost plot, oxygen and iron. Here, the oxygen in each case was sufficient to completely oxidize the iron, unlike the aluminum, where the oxygen was insufficient to oxidize all of the aluminum. See the difference? So elemental aluminum had to be present. Some of it, at least, was element. You have little bits of aluminum, little particles of aluminum. You get an oxide layer that forms very rapidly. It's called passivation, and that occurs on the surface and actually protects the interior aluminum from being further oxidized. Sorry, science. And to me, this is exciting. You look at that and you say, whoa, there's aluminum in there, elemental aluminum. It's not aluminosilicate because the silicon's separate, and there's iron oxide. This is not just elemental iron. We didn't find any evidence of that in the red material. So now we go on higher magnification, 50,000 power. It's Dr. Fair pushed it up, and this, he was the first to see this. I'm just getting goosebumps here again. I mean, I just, you see these grains. Can you see the extreme right there, the bright spots? And you see them more in the, like the center of the SEM image as well. These are grains, and they happen to be rich in iron and oxygen. And the aluminum is found in these plates. Can you see right near the center below that set of grains, there's aluminum. And then around this, there's this kind of a wavy material. This is an organic matrix rich in carbon. Now, this red material is most interesting to us because it has aluminum inside these plate-like structures. The plate-like structures are quite uniform in thickness from what we can observe with the scanning electron microscope, 50 nanometers wide. Plus, the iron oxide appears in these ultrafine faceted grains, approximately 100 nanometers across, and again, very uniform. Again, let me emphasize, this is not from the building collapsing with, sure, there's aluminum and iron and titanium and calcium and sulfur and zinc and copper in the building. But that's not what you see here. Here you see uniform, right? Grains. This is engineered material. I just, you know, if you're a scientist, you just can't say, well, randomly, you know, the building falls down and we're going to get a few of these things. No. And we get 9 tons of this stuff, so we extrapolate. So there's not building stuff randomly mixed together. But what can it be? Okay, now we'll discuss the thermitic reaction, which involves aluminum, elemental aluminum, and iron oxide, which are present in the red material. When these are ignited, as I show in this little demonstration experiment that I did, aluminum powder and iron oxide powder, you get aluminum oxide. Can you see the white plume wisping away above the molten iron? The molten iron is a yellow-white hot coming out of this reaction. It's extremely hot, and you get molten iron. You notice you start out with iron oxide, but you end up with iron. What happened? You start out with aluminum and end up with aluminum oxide. Can you see what's happening? The aluminum grabs the oxygen from the iron oxide, and you get the end products, aluminum oxide, much of which comes off in this plume. It looks like smoke, except it's white. It's quite bright, and it floats away, fine white plume. And the molten iron then form, reduced iron. We'll see, but I want to just say now, while we're thinking about it, that this red material, when we ignite it, we get iron spheres. Many of these spheres are nearly pure iron. Not enough oxygen in them to be iron oxide, you see, less than 1-to-1 even. So we get molten, because it was spheres, now iron that are formed from the red chips when we just heat them up to about 430 centigrade, as we'll see. They react and release a lot of energy, and then we get molten iron. Folks, this is the signature for a thermitic reaction. And we nailed it. It took a long time to nail it, but we did it. We nailed it. One thing I'd like to get perfectly clear, if I can possibly, and I wish there's someone here from NIST who would listen to this. Thermite, I agree, is an incendiary, ordinary thermite, which means powders of aluminum and iron mixed together, and they burn as incendiary. So you see this molten material. This is ordinary thermite here in the photo, and you see the molten iron coming out of that. It's an incendiary. It melts things. But the ultrafine grain form is an explosive. It reacts very fast. The smaller the grains, the faster the reaction. That's been demonstrated in published papers. And we see, for example, this is from a Lawrence Livermore National Lab. Anybody here from Livermore? I welcome you. I'd like to discuss this with you. In fact, we have been in contact with Dr. Tillotson. Dr. Fair has been in contact with him. Haven't learned too much yet, but they've published papers, as we'll see. To me, this is quite exciting. In the lower right, you see the explosion of this. It's called nanothermite or super thermite. This is the ultrafine grain. Okay, now a quick quiz. Super thermite is A, incendiary, or B, explosive? B. Okay, very good. Now, actually, you can tailor nanothermite, which is interesting, so that you can make it react faster, slower, louder. It just has all these variations. You can tailor it. But it can be explosive, is what I'm trying to say here, as you see from the photo from Lawrence Livermore National Lab. I had a BBC crew came through the lab, took photos, videos, of me and I think others in the lab as we worked on these red-gray chips. And interestingly, they asked Livermore if they could show this a photo from a published paper, and Livermore declined, would not allow them to show nanothermite exploding, but it does, you see. It's very important. Here's what I was looking for, this wonderful map. This is in the paper, so you can study it. A little bit of homework on your free time. It's just, again, just so exciting. Dr. Fair took these maps. Isn't that, whoa, look at that, you know? So what are we looking at here? Upper left is an image through the electron microscope. You see the bright grains. How do you know they're iron and oxygen? Well, you look at the blue picture. That's for Fe. In other words, we're scanning over, looking for iron, looking for blue. The purple is aluminum. The green is oxygen. The light blue in the lower left corner is silicon, and the red is carbon. So you see where these things lie. And what we see is that we have iron oxide and aluminum, although here you can't tell real clearly whether it's aluminum oxide or not, because there's so much silicon associated with the aluminum as this stuff is constructed and engineered. It wasn't until we did the MEK separation that we found the aluminum pulled apart from the silicon oxide, and that we're able to nail the presence of metallic aluminum. Again, you can look in the paper. There's another SEM map there. But again, we have this intimate mixing of iron oxide and aluminum, and this very tiny grains of this oxidizer. It goes back about 10 years before 9/11/2001. Certainly long after the buildings were constructed. I get that question. No, it could not have been put into the buildings when they're constructed because it had not been developed at that time. It's a new high-tech technology. And here's some of the uses. Livermore report in 2004, they go on. By introducing a fuel metal such as aluminum into the metal oxide silicon oxide matrix, energetic materials based on thermite reactions can be fabricated. I'm not making this up. This is, these national labs explaining this wonderful explosive material. Organic additives, hence the carbon observed, can cause the generation of gas upon ignition of the materials, therefore resulting in a composite material that can perform pressure volume work. Boom, right? Explosive work. Method, and they describe a method of making nanostructured energetic materials, specifically explosives, propellants, and pyrotechnics, nanothermite. I'll let you read some more in the paper. Read the last paragraph. We have prepared fine powders, pressed pellets, cast monoliths, and thin films of the hybrid inorganic/organic energetic nanocomposite. Hence, we expect to see carbon, that's the organic portion, along with iron oxide and aluminum, just as we observe in this exotic, highly engineered red material. So, it has the proper ingredients for nanothermite, has organic and inorganic. How does it compare with known nanothermite when ignited? Let's heat it up like they do at the national laboratories and find out. So here's what we did. It's done by Dr. Fair. The blue curve, the red done by Tillotson et al. At Lawrence Livermore National Lab. The red curve then is known nanothermite, and we see a temperature. So in this differential scanning calorimeter, it's on the quiz, okay, DSC. Okay, so you heat this material, any test material, slowly. In this case, we use their conditions, 10 degrees centigrade per minute in air, and you heat it up, and in their case, the nanothermite, they made it, they know what it is, that's the red curve, goes off at just about 500 centigrade. In the case of this, and the peak there is actually quite narrow compared to regular thermite. It's also at a lower temperature. I'll show you that in a minute. You know, this is the way we can distinguish nanothermite another way from regular thermite. The red chip, the red material from the World Trade Center dust, I can't remember. Yes, it says McKinley. This is a McKinley sample, Jeanette. And look at that, very narrow and goes off at about 430 centigrade. A little lower in temperature. The finer the material in general, the lower the temperature at which it ignites. The narrower the peak, the more explosive, you see, the faster the energy release. The World Trade Center red-gray chip ignites at a lower temperature than ordinary thermite, and it's narrower, this is called an exotherm, than even known nanothermite from just down the road here, Lawrence Livermore. At the Energetic Materials Center, Lawrence Livermore National Laboratory, published in this proceedings. On the left, you have ordinary thermite. On the right, you have nanothermite. If I can help you read the scale, the ordinary thermite goes off at about 900 centigrade, and their nanothermite goes off at just below 600. It's like about 550 in this case, centigrade. Again, the finer the material, the lower the temperature. So that distinguishes, again, nanothermite from ordinary. Notice how much broader the ordinary thermite peak is compared with nanothermite. This is like no paint you've ever seen before. Let's review quickly. The red material will not dissolve in MEK. This is after 55 hours. There's this hard chunk left. I've got a photo of it down at the bottom. It's highly porous, high in silicon. This skeletal silicon oxide matrix remains after long soaking, whereas ordinary paint dissolves. Resistivity differs. It's attracted by a magnet, the red material. It has carbon, silicon, oxygen, iron, and elemental aluminum, but no zinc on a clean surface, no magnesium, no manganese to speak of, no titanium, no chromium. So I'd like to see a paint that has that. Of course, it might be a fairly explosive paint, you see, as we're finding out. The iron oxide is in quite uniform grains that are approximately 100 nanometers across and faceted. The aluminum is found in plate-like structures. Again, I'd like to see a paint like that, but don't bring it too close to me when it's dry, please. Further tests that characterize these red-gray chips and therefore characterize the World Trade Center dust. You see, now we can tell when we've got World Trade Center dust because it has these striking, unusual red-gray chips in it. The red layer ignites at about 430 centigrade. The DSC trace is narrow, and it produces iron oxide spheres. Again, I want to point out, as we observe, that these are uniform grains, intimately mixed, nanoscale, narrow exotherm. This is an engineered material. This does not happen just from a building collapsing. I should add, we actually looked at dust from ordinary controlled demolition, so you have then this collapse of buildings caused by explosives, but ordinary explosives like C4. We looked at the dust in some detail, Daniel Farnsworth and I. for red-gray chips. This was the demolition then of the Stardust Resort in Las Vegas. No red-gray chips at all, and we plowed through a lot of material. Same way with the Key Bank in Salt Lake City. These are discussed in the paper. These are controls, and no red-gray chips in the controls, okay? Just in the World Trade Center dust that we've seen. Okay, oh boy. You can read some of this in the paper. I'll let you do that, but this is from an April 2001 conference in San Diego, and they say in the middle here, the breadth of the work ongoing in this field of nanothermite and other related nanoenergetics is roughly 10 years old, so it goes back to about 1991. It was available by, obviously, by 2001, when this conference was held in April. At this point in time, all of the military services and some DOE and academic laboratories, and certainly overseas laboratories as well, have active R&D programs at exploiting the unique properties of nanomaterials that have potential to be used in energetic formulations for advanced explosives. These results were published in MTAC Quarterly, Department of Defense publication, I understand. And as we look at this, that's what I was just quoting from, this meeting held in April 2001. Now look, this is from the article talking about the uses of this advanced energetic material, this nanothermite, for example. At the top, you see kinetic energy munitions. In the middle, you see thermobaric applications for nanothermite. And at the bottom, you see a very interesting application, a shaped charge. This explosive material can be formed into a shaped charge, just like C4, and can cut through steel, not melt through, right? You see the difference, right? Ordinary thermite is incendiary. Nanothermite can be formed into an explosive shaped charge. Now, it's not easy to make this stuff. This is again from the report making the nanoscale aluminum for these high-tech explosives. This was done at a naval facility. Incidentally, again, this material could well have been outsourced. I'm not saying it was necessarily done even in this country. That's a very interesting question, where this stuff was made and who made it and who ordered it made and who put it into the building. Those are the crucial issues. This shows what is required to put these materials together. Very high-tech process to intimately mixed ultrafine aluminum with ultrafine iron, again, out of this MTAC report. How much material was in the dust? I want to go through this argument quickly. We report in the paper, the first paragraph is a quote from the paper, 15 small chips having a mass of 1.74 milligrams, extracted from a 1.6 sample of dust from which readily identifiable glass and concrete fragments had been removed by hand. The fraction then of red-gray chips was approximately 0.1% by weight in the separated dust. The unseparated dust is about 3 times that. A rough estimate of the amount of dust from the WTC destruction is estimated. I refer to work by Gregory Urich, 90,000 tons. He sent me an email actually about that. That brings us to about 27 tons of the red-gray chips in the dust. Again, this is just based on what we observe in this sample. There's a lot of material. If you just look at the red material alone, it's about 1/3 the mass of the red-gray chips, which works out then to about 9 tons of active thermitic material. A very rough estimate, as I must emphasize. Our conclusion is that we have found a very energetic, highly engineered, explosive, pyrotechnic material in the World Trade Center dust in abundance. The questions now are, who made this stuff? And why has NIST refused to even look for World Trade Center explosive residues? Also, USGS have asked them. They have not replied. Will they do so now? Now, I want to foresee questions. I don't know exactly how this material was used. I've given some hint, but I don't know. It could be, as we explain in the paper, that just the thin material survived and that thicker layers of this red material were actually used in the building. The point is there's a lot of it, and it should not be there in a commercial building occupied by humans. Details of exactly how they used this to destroy can be learned once we find out who made the stuff in multi-ton quantities. Subpoena power is needed. Again, once you find an accelerant in these photos, thermite was found in the residues of this fire. It proves that there was arson, there was intentional destruction. That's what we have in this case. We have these identified now materials in the World Trade Center dust. The U.S. government oversaw, I think it's fair to say, someone certainly allowed the destruction of 99+% of the World Trade Center steel. That evidence was destroyed. We want to prevent this from happening to the World Trade Center dust. So my concluding slide, the international 9/11 truth movement and community is strong and growing. We can support the New York City CAN referendum. I like that. New York City can do it. They can initiate this investigation. There could be other places, like an international group of scientists, to investigate the World Trade Center dust, for example. We can point people to published papers, their DVDs. It requires of us courage, I believe, and love and truth to take action with civility. And let me just say in closing, just in case, please get your food storage. Thank you.
Like the scientific evidence obtained from crime scenes every day, the scientific evidence that Stephen Jones' team has recently uncovered is admissible in a fact-finding commission or a court of law. It is scientific proof of the specific weapon used to kill 3,000 people.
Thank you.